So welcome back. This is our third lecture about the learning parameters for Bayesian networks from data. And now let's take a look on the expectation maximization algorithm. So let's work with a numerical example that will make things more concrete to us. So we have a data set, we have the structure, and we have the parameters here. So, we'll work with the EM algorithm, and this expectation EM algorithm will be an iterative algorithm. So we're going to denote here with those zeros here that these are the initial parameters that we have, and we'll try to improve those parameters with the EM algorithm iteration by iteration. So how we compute those initial parameters? So we can try different techniques. One of them is to try to best estimate them from data and try to improve with the EM. We can complete those with random numbers, but we need to be very careful because we cannot just use random numbers. We need to make those numbers to make sense from the probability distribution perspective, right? So those numbers need to sum to 1. The conditional probabilities for a certain conditioning, when we fix the condition, they must sum to 1, and so on. So we need to be a little bit careful, but we can start with some estimation from the data, and for the variables that we cannot estimate, we can maybe fill in with random values as far as those numbers make sense from the probability distribution perspective. When we have those initial estimates, we needed to compute the likelihood for this Bayesian network. So we need to compute how well that network will explain the data set. So we have the data set here, really small, with just 5 cases. We know how to compute the likelihood. That's going to be this function here. So I'm not using the log likelihood, I'm just using the likelihood. It's going to be simpler to compute, but in practice we usually use the log likelihood. So it's going to be the multiplication for 5 cases that we have, so this number 5 here. The probability, take a look here, the theta 0, that is our first estimate for each case that we have the I. So for example, for this first case that we have here, we have 2 missing values, one for variable A and another one for variable D, and we have the values B and not C. So when we compute the probability for this case here, according to the Bayesian networks and the initial parameters, we need to compute this probability here. Take a look that we are not mentioning the variables A and D because we don't know the values for those variables. So we need to compute the probability of B and not C. And take a look that the probability of B and not C is not readily available in the tables that we have here in the parameters, so that will involve inference of the Bayesian network. So basically this is a probability query. It's a very simple prior marginal query that we needed to sum out the variables A and D in order to compute this. And if we compute, the number is going to be this one, 0.135. And we're going to do the same for the other entries that we have here in the data set. So we're going to take each of the case and going to compute those probabilities. So you probably noted that what we are doing here is more complicated than what we did for the complete case. And for the complete case, things were easier because we did not have in the missing values, so we did not had to do any inference in the Bayesian network. So for instance, if you have a complete case that involves A, B, C, and D, just to make it a little bit more concrete, so we have like A, B, C, and D, so it's a complete case because we have these 4 variables, so it's going to be true for all of them. What we have to do in order to compute the probability of A, B, C, and D given these theta 0 parameters is only to look at the entries of the table that conform with this assignment. So we're going to multiply 0.75 because it has A and B true. I'm going to multiply this number by this guy here, 0.5, because it has A and C true. I'm going to multiply by this entry here because it has A true. And I'm going to multiply by this entry here because it mentions B and D true. and the multiplication of 0.75 by 0.5 by 0.2 by 0.2 is going to be the probability of A, B, C, and D. But now what we have is an incomplete case, so we only have B and not C. In this case, we cannot directly multiply the entries that we have. We have to do a little bit of inference, because what we have is B and not C. So this we will have to consider this entry and this entry here, because both mention B. We have to consider this entry here and this entry here, because both mention A. We need to take into account these two entries here, because it mentions A and not A, and we have a missing values for A, so we have to consider both of them, and we have to consider this entry here because it mentions B, and this entry here that mentions B. So we will put all those numbers together. We're gonna submount the variables A and D because they have a missing values, and we will end up with the probability of a B and not C. So as we can see, there is a lot more working when we are computing those probabilities for incomplete case, because we are doing a little bit of inference here. But we can do it, and if we do, we can multiply all those probabilities together. So take a look at that. In this case here, we will need to sum out two variables. In this case, we need to sum out only one variable, this only one variable, and in this case, two variables A and C. And if we do that, we end up with those probabilities here. These are the probabilities for each of these examples, and we can multiply them together, and we have this very small number here that represents the joint probability for all the samples that we have in the data set. And that is the likelihood for this Bayesian network, these initial parameters. And now we're gonna update those parameters in a certain way that are going to increase or keep the same likelihood. And that is the basis for the expectation maximization algorithm. So the expectation maximization algorithm is very similar to the complete data method that we studied in the first video. So just to summarize how the EM algorithm works, and we're going to see one example in the next slide. It first completes the data set inducing an empirical distribution. And let's suppose that now we have the complete data set, and we're going to see exactly how we do that. But imagine that we have the complete data set. What we can do is estimate the parameters using maximum likelihood. And we know that when we have the complete data, the maximum likelihood estimates are very simple to take. It's just the counts of the frequencies that we get from the data. And one very interesting and important property of the expectation maximization algorithm is the fact that the new parameters that we're going to use in the next iterations, they are guaranteed to have no less likelihood than the initial parameters. So we're going to improve those parameters by doing this process. And we're going to repeat this process over and over again until we have some convergence condition met. We can think that this condition will be to have those parameters not changing anymore, so there is no reason to continue iterating because they are not changing. But frequently what we do is to set a threshold, and when the change is smaller than this threshold, we just stop iterating because they are moving really slowly, and we have already some good estimates for the parameters. So the main problem now is how to complete the data set, so we can use the complete techniques that we know in order to estimate the maximum likelihood parameters. And we're going to see that we don't know which is the completion of the cases, but we can make inference over the Bayesian network in order to compute them. So let's take a look at, for instance, in the first sample here. So we don't know the values for A and D, but we can associate the values with A and not A. We have B and not C. These are guaranteed to hold, so we need to keep them. And we don't know the values for D, and it can be D or not D. The truth is that only one of these 4 possible assignments, right? Because we have 2 possibilities here, we have to keep this constant, and we have these 2 possibilities. So we have A, B, not C, and D. We have A, B, not C, and not D. We have not A, B, not C, and D. Not A, B, not C, and not D. So we have these 4 possible assignments, but only one is true. But we don't know which one is true. What we can do is to compute the probabilities for each one. And we can use the Bayesian network in order to compute those probabilities. Let's take a look at how to do that in the next slide. Okay, so this example here illustrates how we can compute the completion of the cases. It's the same example that we had in the previous slide. So what we're going to compute is this conditional probability here, where these CIs here are the variables with missing data, and the DIs are the case that you want to complete. So for instance, we have the case D1, and the D1 has 2 variables with missing data. So we don't know the exact values for the variables A and D. So we can make the possible completions A and D, A not D, not A and D, and not A and not D. And we want to compute the probabilities for each of those instantiations. So what we do, we fix B and not C, because this was observed, right? So this, we know this from the example D1. So I'm going to fix that, and I'm going to compute the conditional probability for each instantiations of A and D given B and not C. So for instance, we have A and D given B and not C. So it's going to be 0.111. So we have to do a little bit of inference. We have to do inference in the Bayesian network in order to compute this result. And we move on and we compute for the other possible entries here. So the second case here is going to be the probability for the parameters theta 0 of A and not D given B and not C. So B and not C is fixed, and the other ones are the instantiations that we have here, 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 and here. Right? So you're going to compute all those conditional probabilities. Take a look at that. These conditional probabilities must sum to 1, right? Because we have fixed the conditioning. So we're only changing the variables that are in the left part of the bar. So if we go through all possible instantiations, in this case of A and D, the probabilities will sum to 1. And that is very good because we can assign a weight 1 to each possible sample that we have in the training set. So this guy D1, we want to have weight 1. D2, we're going to have weight 1 as well. It has 2 variables with unknown values. It's going to be A and C. So we complete with all possible instantiations. D3 has only 1 variable with missing data, that's A. So I'm going to do all the possible completions. But this conditional probability here, that is actually incorrect because it's probability of A given not B, C, and D. So sorry about this. And this one's going to be the probability also given theta 0 of not A given not B, C, and D, right? So these 2 conditional probabilities also must sum to 1 because we have a fixed not B, C, and D. We are only changing the A and not A, that AT is in the left part of the conditional bar. And we do that for all the cases that we have in missing data. So now we have those weights associated with each possible completion of the samples, and we can now compute what we call an expected empirical distribution. So in order to compute this expected empirical distribution, what we're going to do is very similar to what we did for the empirical distribution, but instead of working with cases, now we're going to work with those probabilities. So we're going to take all possible instantiations of the variables, and we're going to count now the sum of the probabilities instead of the sum of the number of examples that we had before. So just looking at one concrete example, let's suppose that we want to compute the probability of this instantiation here. So what we're going to do is the following. Let's just erase this. That's going to be too messy. We're going to look for where we can find cases that mentions the variables a, b, not c, and not d. And this case can be complete case. In this case, the weight will be associated will be 1, or it can be these completions that we made for cases that had missing values. And in this case, we are not going to sum a weight 1, we're going to sum a weight that is smaller or equal to 1. So let's see what we can find here. So we have a, b, not c, and not d. So we'll find this guy here. So in this case, we're going to sum 0.444. This comes from a completion, so it's not a complete weight, so it's not weight 1. We're going to find a, b, not c, and not d. We're going to find it here. So we're going to sum 3, 2, 6. And for d3, there is no match. For d4, there is no match. And for d5, there is a match, a, b, not c, and not d. So plus 0.326 again. And when you divide this by 5, that's the number of instances that we have from d1 to d5. So let's illustrate this in the next slide. So here we have the same computation, but now with a little bit more detail in the equations. So we want to compute this probability of a, b, not c, and not d. So this is our instantiation, and it's saying here that's going to be the sum of those conditional probabilities, and those conditional probabilities are basically the rows that we have marked here in gray. So for this case d1, we have this instantiation that matches the instantiation that we are looking for, a, b, not c, and not d. And in this case, this conditional probability is the following. It's going to be the probability of a and not d. These are the two completions that we made, given b and not c. That is fixed because this came from the case. Exactly what is being expressed here. I'm going to sum also this guy here that has fixed b and not d. So we see that we have b and not d here, given the instantiation a and not c. So we have a and not c, given given b and not d. And finally, we have this instantiation here on the bottom, where the fixed variables are b and not d. So b and not d here, given the completions a and not c. A and not c. So we have the probability of a and not c given b and not d. So take a look at that. We are using this notation here. It's saying that this probability comes from a Bayesian network that has this parameter theta 0. So it's going to be the first iteration of the EM algorithm. And when we compute this, we get this number here. Take a look that we divided by 5. That's important because we are summing those numbers. They sum more than 1, and we need to divide it by 5. That is the total number of cases that we have here. So at the end, we have this probability here for this complete assignment. So we have to do this for each complete assignment that we have in the expected probability distribution. Remember that this expected empirical distribution is a joint distribution over all the variables. So in theory, we have to look at this exponential number of instantiations and complete all of them. We're going to see that in practice, we don't do that, right? So we jump this step and go directly from the parameters that we have in the Bayesian network. We do the inference and we go directly to the parameters that we're going to use in the next iteration for the Bayesian network. So we don't have this middle step of computing this expected empirical distribution. So we have here the same idea expressed with one equation. So what we are saying alpha here is going to be one complete instantiation that we have in the empirical probability distribution. And we have this 1 over n. N is a number of cases we have in the data set, and we have the summation that we have here on the top for all the cases that match the instantiation. So we're going to look at this table here and we're going to see which cases they match the instantiation alpha. And in order to match the instantiation alpha, we're going to have the complete variables that came from the training set, and also the completions that we did for the variables that have missing values. And so we have to match this. So for each case here, we're going to find possibly one row that have this match. And we compute this probability here that depends on the Bayes network and the current parameters that we have. So it's going to be the probability of CI, that are the variables with missing values that we completed, given DI, there are the variables that were already complete and present in the training set. So this equation here is basically the same thing that we computed here. So remember that we have to do this for different alphas. So we're going to have an exponential number of alphas. So that is not very efficient from the computational perspective, but we're going to see that we can jump this step and go directly from parameters in one iteration to the parameters in the next iteration. So here we are illustrating this idea. So this is our expected empirical distribution. These are all possible instantiations that we can have. We have 4 variables. They are all binary. So in this case, we have a total of 16 possible instantiations, 16 possible combinations of values for these variables. We have computed one row for this distribution, that is this A, B, not C, and not D, with 0.219. We did that in the previous slide. We have to repeat these computations for all the older instantiations. At the end, we have this joint distribution here. When we have this joint distribution, we can now compute the parameters for the next iteration. So let's suppose that we have this parameter here in our Bayes network. So it's the conditional probability of a C given and not A. So we need to compute this guy here, right? So we know from the Bayes conditioning that is going to be the probability of C and not A given over the probability of not A. And in order to do this, we have to come here to our empirical distribution and look at the rows that are going to match this. So we have A, not A and C. So not A and C, we have this row here and this row here. As well, we have this row here and this row here. So basically, we're going to have this ratio, and I'm going to eliminate the other variables, but at the end, we have this sum of 0 plus 0.35 plus 0.351 plus another 0 that I'm not going to write here. And we also have the probability of not A, and the probability of not A is expressed by those rows here. And we're going to have the sum of all these values, so it's going to be 0 plus 0.035 plus 0.018 plus 0.176 plus 0.351 plus 0 plus 0 plus 0, right? So you're going to have these two guys here, and going to have is the sum of these two terms. On the top here, we have 386 over, in the bottom we have 0.580, and we compute this ratio here, and we're going to have this number 0.666 here, right? So we have computed this parameter, the probability of C given not A. So we have to do this process for each parameter that we have in the Bayes network, and at the end we have computed all the parameters. Once we have finished with that, we go to another iteration, and we go over this process again. So just to remind you, we're going to take these new parameters and starting doing inference to complete the cases with missing values that we have in the training set. Now the completions will be different because we have new parameters. So when you compute those conditional probability values, those probability values are going to be slightly different from what we had before, given that we have new parameters now. And once we have completed the cases, we have the expected empirical distribution, compute the expected empirical distribution, and from the expected empirical distribution, we computed the parameters for the next iteration. And we keep on doing this until we have convergence. So until the values of the parameters, they don't change much, less than a certain threshold, and we stop that. So okay, here we have a new set of parameters for our Bayesian network. So here is the Bayesian network, and these are the parameters. Take a look here at the numbers 1 here, indicating that we have a new set of parameters. And there is one guy here that we already know, that is this probability of C given not A, that's 0.666, that we computed in the previous slide, and we have to do this for the other parameters of the Bayesian network. So once we have the parameters, we can compute the likelihood. We don't do this process because the expectation maximization algorithm it's guaranteed that each iteration we're going to improve or at least keep the same likelihood that we had in the previous iteration. So as we have this guarantee, there is no reason for computing the likelihood again just to confirm that we are improving the likelihood. So that's going to be an extra computation, but there is no reason for doing that. But of course, here in the slides, we can do this just to confirm and look at a numerical example and grasp a little bit more intuition about this computation. So if you want to compute this likelihood for this parameter set theta 1, and given the data set, what we have to do, we have done this before, is to look at the cases here and compute the probabilities for each case. So we're going to take a multiplication for the 5 cases that we have, the probability of di given, not given, but based on the set of parameters theta 1. So we have these numbers here being multiplied. Just to remember what those numbers mean, basically they are the probabilities of the cases here given using the information that we have at hand. So for the first case, we're going to compute the probability of B and not C. For the second case, the probability of B and not D. For the third case, the probability of not B, C, and D. For the fourth case, we're going to compute the probability of not B, C, and D. And for the last case, we're going to compute the probability of B and not D. So these numbers are actually those probabilities, and we have to do a little bit of inference over the Bayesian network in order to get those numbers. Okay, and when we multiply these 5 numbers, we get this result here. That is 5.9 times 10 elevated to -3. And that is larger than the likelihood that we had for the first set of parameters. And I don't remember the number exactly, but I do remember that it was something times 10 elevated to -5. So yeah, we have improved this number here quite a bit. And we go to the next iteration, and it should improve this number a little bit more, and so on, until we get into convergence and we stop the process, we stop the algorithm. And here, just one more equation, just to make things more concrete. I'm sure that you already understood the idea, but the parameters that we have for the next iteration of the Bayesian network. So take a look here that we are making reference to this x given u. So x is each variable that we have in the Bayesian network given u that are the parents. It's going to be defined by the expected empirical distribution that we computed with the previous iteration of the parameters, the theta k, and now we are computing the theta k plus 1 of the x given u. So it's going to be the probability of x given u. So basically saying that those parameters here are the counts that we got from the expected empirical distribution that we computed with the previous parameters, and we keep in doing this process. Okay, so as I said before, when we compute the parameters for the next iteration, we do not build this expected empirical distribution, because that expected empirical distribution is going to be exponential over the number of variables. So what we do, we go directly from one parameter to another parameter by doing inference over the Bayesian network. So in the previous slide, we make this definition here. So we defined that the theta for the next iteration, k plus 1 of x given u, is defined as the empirical, the expected empirical distribution, d theta k x given u, right? So this was the definition. So when using this definition here, what we can say is that this guy here is going to be a ratio between the probability given by the expected empirical distribution, x and u, divided by the probability of u, also given by the expected empirical distribution. But when we have these two things here, and we know that from the previous slides that we can compute those things by using this equation here, basically is a sequence of probabilities, conditional probabilities that we sum over all the cases that we have, we can go directly from this guy here to this guy here, right? Without mentioning this expected empirical distribution. So what we can do is just take this equation here, that's 1 over n, the sum for over all the cases, I equal 1 to n, the probability of the instantiation alpha given di. So in this case here, going to be xu given di over this 1 over n, also the sum for all the cases that we have, the probability that we compute using the parameters k from the Bayesian network, and now here the instantiation alpha is going to be just u, so going to u given di, right? And we can cancel this 1 over n, and we end up with this equation here, right? So in this case here, what we are doing, we are coming from this parameter here for the next iteration, using to compute the parameters that we have in the previous iteration, but without making reference to this expected empirical distribution. And just to look at one example to make things more concrete, so we have computed this parameter here, c given not a, and we can now do this directly, jumping the expected empirical distribution by computing this ratio here. So these are the sum for the case, and these are the completions that we needed. They needed the completion c and not a. So we have 5 cases, and take a look that we have the 5 conditional probabilities here. Take a look, the first one is 0 because it's not possible to have instantiation for c here because we have read the not c for the training data. But for the older instantiations, it's possible to have c and not a here, c and not a here, c and not a here, and c and not a here. So I'm going to have non-zero probabilities for the main ones. For the denominator, we have the not a, that is the parent. So for not a, as a is a latent variable, we can have a not a for all instantiations. So I'm going to have conditional probabilities different of 0 for all the 5 cases. We sum numerators and denominators and take the ratio, and we have the 0.666 that we had before. So this is going to be the parameter for the next iteration, and we do these same computations, so similarly by using this equation here for all the parameters that we have in the Bayesian network, and we got the new parameter set. So this is the EM algorithm, the expectation maximization. Let's take a look at how it works, but basically going to be an application of the equations that we discussed so far. So we have the variable k that we're going to initialize with 0. So k is the variable that controls the iterations. We have the initial set of parameter values that are going to be the theta k. So we need to decide how we're going to initialize the values. One possibility would be with random numbers. Another possibility would be with computing the values with the data. So we look at the completed data and try to estimate the conditional probabilities for the Bayesian network as best as we can, and we fill in the gaps with random values. But in any case, we need to be a little bit careful in order to make the numbers to make sense, right? So I mean that if we have an unconditional distribution, we need to make the numbers to sum to 1. If we have conditional probability distributions, we need to look at each conditioning and make the values to sum to 1 too. So we need to be a little bit careful when we set those numbers. The next step is going to be this while loop here that we're going to iterate while we do not reach convergence. So there are many ways to establish convergence. One of them is to look at the parameters in 2 consecutive iterations and measure the difference. And if this difference is very small, we can stop the algorithm and say that it has converged. One problem with this approach is that we have many parameters in a Bayesian network. So most of them may have converged, but a few of them are still converging. And when we look at a general number, we may miss those details and establish convergence, but yet we have some parameters that are still converging. Another criterion that is also very used, but that will give us a little bit of overhead, is to use the log likelihood. So we can compute the log likelihood and see the difference between the log likelihood in 2 consecutive iterations. If this number is very small, we establish convergence. And the next step is to set this counter here, CXU, to be 0. And that's going to make this for each family instantiation X and U. So for Bayesian networks, we are interested in estimating the parameters, and we know that parameters are tables for each variable and makes reference to this variable and also the parents that we have. So this this CXU is going to be like small tables that they make reference to all the possible values of X and the parents U. So we can think like we have estimated a parameter that was involving the variable C and A. So we can think that this XC for the variables C and A is going to be a small table. We're going to have 4 entries because we have 2 binary variables, and we have like C, C, and not C and not C, and we have A and not A, and A and not A again. And for each entry here, we're going to have a value 0, right? So and we're going to have one of those tables for each family that we have in the Bayesian network. And now we're going to make a pass over the data. So it's going to be a single pass. So I'm going to go from 1 to n, b n the number of cases that we have in the training set. And again, we're going to do this for here for each family instantiation XU that we have in the Bayesian network. And now we're going to update the counts by summing this conditional probability here. That is basically the probability of the completion of each case. So we're going to use the parameters that we already have in the Bayesian network in order to compute this, and we have discussed how to do this in the previous slides. So once we have finished with that, what I'm going to do is to compute the parameter. So this parameter X given U will be given by this ratio here. So this is one interesting trick in order to make the computations more efficient. So if you were looking at this computation here, we have this. They have this parameter at the iteration k plus 1 x given u, and that's going to be equal to this cxu, and should be divided by the c of u, right? And that's going to be the ratio between the sum for all examples that we have for this probability here that we need to do inference over the Bayesian network in order to compute this over another set of probabilities that we would need to make inference over the Bayesian network again, right? But we can actually eliminate this part of the computation, right? And we're going to gain efficiency by doing that because we don't have to do this double inference for each parameter. And the trick here is to do the case analysis. We can get this probability here by computing a sum over this probability here. So basically, by case analysis, if we sum over all possible values of x, we can get this probability here, right? So just to make one concrete example, we were computing the probability of C given not A. So I can compute this by using these counters for C and not A, divided by 2 counters that are going to be the counter for C and not A plus the counter for not C and not A. So we are summing over all possible values of C. So that's why we call this CXU here a sufficient statistic, because from this information CXU we can compute all the numbers that we need in order to compute the parameters for the next iteration. Okay, so returning to the algorithm, so we compute here the parameters for the next iteration by basically doing this ratio that I illustrated here with one example. We update the variable k that controls the iteration that we have, and we go up to the while loop and we test for convergence again. Once we have finished with that, we return this set of parameter values that are going to be the theta k. So we have here a few observations about the EM algorithm. The first one is that the algorithm may converge to different parameters depending on the initial estimate, the theta 0. So it's very common to run the algorithm multiple times, starting from different theta zeros and see where we get. And of course, we have a measure of quality that is the log likelihood. So at the end of each execution of the EM algorithm, we can compute the log likelihood and compare these different executions and take the one that gave us the highest value for the log likelihood. And the second observation here is that each iteration of the EM algorithm will have to perform inference over the Bayesian network. So it means that we need to compute the probability of each instantiation, XU, given the complete case DI that is used as evidence. So these computations correspond to this, what we call the posterior marginals over the network families. And an efficient way to compute this is to use the join tree algorithm, because the join tree algorithm will give us the marginals over all the families that we have in the Bayesian network. So with just one execution of the join tree algorithm, we'll get all the marginals that we needed to use to make the inference over one single case. And we can use the idea of resend messages to update for different cases that we have in the training set. So the join tree algorithm will be very efficient for this case, and it is the standard implementation that we use when we are implementing the EM algorithm. All right, I think that is good for this video. Let's make a pause and continue in the next one, when we're going to discuss a little bit more about the missing data mechanism. See you soon.